Hi, I'm Charles Feddersen, and in this talk, you're going to learn about all of the ways that we're driving Postgres forward at Microsoft through open source, cloud services, and building amazing tooling for developers and database operators.
Hi, my name is Affan Dar, and in this talk, you will learn about how Microsoft is contributing to the open source Postgres project.
Hi, everyone. I'm Charles Feddersen. I'm the Director of Product Management for Postgres at Microsoft. Welcome to Posette 2026. Today, I'm joined by Affan Dar, who's the Vice President of Engineering for Postgres at Microsoft, to talk about the different ways we're working to drive Postgres forward at Microsoft. But before we get started, I'd like to quickly reflect on our Posette journey. We're now in our 5th year running this virtual conference, and it's great to see how Posette has evolved into a recurring event on the Postgres community calendar. When we started Posette, it was a bit of an experiment. There were so many fantastic in-person events for Postgres being run all over the world, and with so much online content, we weren't sure whether a virtual conference would succeed. But 5 years later, the conference continues to grow, with more speakers submitting great sessions and content from past conferences continuing to be consumed. This year, we had a record 238 talks submitted to the event, and content from past conferences has now been viewed over 380,000 times. Thank you, everyone who submitted to speak this year, and we appreciate the time and investment you made to submit these great sessions. And of course, events like Posette don't just happen. This year, we have a great organizing team spread between the US, Europe, and India who balance the Posette workload with their core day-to-day roles. I'd like to thank Aaron, Claire, Cornelia, Gary, Henry, Jeremy, Linda, Pooja, Sriram, and Silvano for their effort to put together this great event. But the hardest task of all is selecting the sessions. As I mentioned, this year we had 238 talks submitted. I'd like to thank Claire, Daniel, Divier, and Melanie for their work to finalize the talk selections this year. Now, for the remainder of the session, Afan and I will talk about 4 different aspects of how we're driving Postgres forward, which includes the open source project where Microsoft is one of the largest committers to the upstream project, Azure services, where we're enhancing Azure Database for Postgres and have just launched the public preview of HorizonDB. And finally, our investments into tooling to deliver AI-enhanced capabilities for database development and management. So to get things rolling, I'm going to hand it off to Afan to talk about open source. Over to you, Afan.
Hi, everyone. I'm Affan Dar, and I lead the engineering for Postgres at Microsoft. First off, when we talk about building Postgres the right way at Microsoft, we're really talking about responsible open source participation at cloud scale. Postgres runs some of the most mission-critical systems in the world, and our responsibility is to strengthen the ecosystem. So through our team of committers and contributors, we engage and deeply invest in core areas of Postgres. Secondly, we have the privilege of running Postgres at a massive scale across the globe. This gives us a perspective on operations, reliability, and tenancy issues that only appear at a very large scale. And our open source team brings many of these learnings back into the upstream project, which benefits the whole ecosystem. Finally, our committers and contributors often engage directly with our enterprise customers running their mission-critical workloads on Postgres to solve operational and sometimes functional issues. This gives our open source teams deep exposure to how enterprises are using Postgres in Tier 0 workloads. Improvements and bug fixes as a result of these interactions go upstream and again benefit the whole ecosystem. In Postgres 19, Microsoft made about 345 commits to the upstream project and changed around 64,000 lines of code. These contributions were made over a number of different areas, but many centered around our work on the query engine, asynchronous I/O, and observability. Let's go over some of these in a bit more detail. Query planning and execution saw notable gains, including row decoding improvements and support for parallel TID range scans. Foreign key checks during inserts will also be significantly faster with the new fastpath, using compiled code instead of incurring SPI overhead. We also co-authored new SQL capabilities with the support for SQL property graph queries that enable native graph pattern matching. This work represents one of the largest single feature additions in the Postgres 19 major version. At the storage and buffer management layer, the team delivered major architectural enhancements, setting the stage for Postgres 20 improvements like buffer elasticity and using async I/O for writes. Updating the visibility map during access will improve index-only scans and greatly reduce wall volume. Finally, the team expanded Postgres' introspection and performance tooling with the new explain I/O infrastructure, which adds visibility for I/O operations. Microsoft also worked on critical CVEs, underscoring our commitment to Postgres security. Uh, Postgres' manageability also becomes much easier in Postgres 19 with automated resizing of the I/O worker pool. Collectively, these contributions strengthen Postgres' performance, envelope, standards compliance, and operational transparency. They also lay the critical groundwork for the next generation of cloud deployments. Now I'll send back to Charles to talk about Azure Database for Postgres. Over to you, Charles.
Thanks, Affan. Now, turning to Azure, we've continued to ship new feature enhancements to Azure Database for Postgres on an almost monthly basis. And while we've made improvements across the entire service, today I'm going to focus on just a few performance, scalability, and uptime improvements we've made to make sure it's easier to run your Postgres workloads at scale. Last year, for the first time, we shipped the new major version of Postgres in Azure on the very same day that the community announced general availability. This meant that our customers had access to the latest Postgres 18 features immediately, without waiting for any cloud lag. And this matters when newer versions bring real gains to performance, like query planning and observability, like Affan just talked about. Azure customers can standardize versions faster, reduce their version sprawl, and keep development production aligned with the community release cadence. Next, we announced the general availability of near zero downtime scaling to address one of the hardest production problems, scaling capacity without interruptions. Customers can now scale compute up or down, and the application just experiences a failover. And this provides significantly improved availability during these scaling operations and helps avoid over-provisioning or static configuration of compute. And for performance, we announced the general availability of SSD v2, which supports up to 64 terabytes of storage, up to 80,000 IOPS, and up to 1.2 gigabytes per second of throughput. But most importantly, these disks support independent scaling of each of these scale points. This enables you to perfectly fit the size and throughput of the disks to your workload. These disks are now deployed in 46 Azure regions today, and you can upgrade from SSD v1 easily using a replica and planned failover. Next, cascading read replicas enable you to extend read scalability beyond a single replica tier. With this feature, replicas can themselves be the source of other replicas, enabling global scale read distribution and better isolation of read queries, which reduces the load on the primary server, reduces read latency for globally distributed applications, and provides architectural flexibility as workloads evolve. Now, to show you how cascading replicas worked, I've asked Gary to provide a quick demo. Take it away, Gary.
Hi, welcome to the demo of Cascading Read Replica. In this demo, I'll walk you through how to create a cascading read replica and then show how to perform a switchover operation between an intermediate and cascading replica. Let's start by creating a cascading replica. This is my primary server. From the left-hand navigation menu, I'll go to the replication blade. On the replication blade, I'll select the read replica server. From there, I'll again navigate to the replication blade and click Create Replica. Since I'm creating this replica from an existing replica server, the source server is now read replica. I'll provide the server name, fill in the required configuration details, and click Create. The read replica creation is in progress. Now you can see the read replica creation is complete. It's listed under Parent Read Replica in the replication hierarchy. Now, let's look at the switchover operation. From the Azure portal, you can click on the Promote button to perform switchover. I'm going to use Azure CLI to perform the switchover operation. Let's do AZ login, then run the command for switchover by adding the resource group name and replica server. The switchover operation is in progress, and now you can see that the switchover operation is complete. The role of the intermediate and cascading read replica are swapped, and the replication chain is maintained. Thank you.
Thanks, Gary. Now, finally, with Elastic Clusters, we brought the horizontal scalability of Citus directly into Flexible Server. Instead of trying to pack large applications into a single Postgres server or implement application-level sharding, which could become complex and to operate at scale. Elastic Clusters, a new feature of Flexible Server, enable you to deploy a cluster of Flexible Server instances to distribute your workload across multiple machines and multiply the throughput of your application. It looks like a single logical database to your application, and you can shard your data in one of two ways, either distributing tables using sharding keys or by the schema where an entire schema resides on a given node. Each approach has benefits and trade-offs, and the best approach will really depend on the nature of your application. Together, these features focus on performance, scalability, and operational simplicity to make Azure Database for Postgres more performant and easier to use. But this is only part of the Postgres on Azure story. A few weeks ago at Build, we launched the public preview of Azure HorizonDB. And we're going to hand it back to Affan to talk about some of the key architectural enhancements in HorizonDB and how we're innovating to make it the best platform for new and existing Postgres applications. Back to you, Affan.
Thanks, Charles. Azure HorizonDB is built for enterprises that need scale, high availability, and modern intelligence without compromise. It delivers elastic scale across storage and compute, enabling you to handle the most demanding transactional and analytical workloads without redesign. Built-in resilience ensures sub-5-second failovers, keeping applications continuously available and minimizing business disruption. HorizonDB is a cloud-native Postgres service built from the ground up with a disaggregated architecture that lets you scale storage independently from compute and share that storage between the primary and read replicas. It supports up to 192 cores with sub-millisecond commit latencies and a sub-5-second failover time. HorizonDB scales up, it scales out across both the compute and storage tiers. Now, let's look at some of the late-breaking AI features that are part of HorizonDB. Vector search and AI capabilities run natively inside the database, so you can build intelligent applications directly on your operational data without moving it anywhere else. Our disk canon implementation gives you better accuracy, higher recall at the same memory footprint. It compresses vectors more efficiently, so more of your data stays in fast memory instead of slow disk. And it computes similarity faster, which means lower latency at query time. We also built AI model management directly into HorizonDB. With a single click, HorizonDB provisions 3 models on Microsoft Foundry, one for generation, one for embeddings, and one for ranking, and wires them directly into the database. Functions like extract, create embeddings, and rank just work out of the box. No setup steps, no glue code, no jumping between services. And if you'd rather bring your own models from Foundry, you can register those too in just a few steps. Every GenAI app rebuilds the same pipeline: chunking, embeddings, sync, retries, backfills. Today, that logic lives in external pipelines, which quickly become fragile and hard to manage. AI pipelines brings that lifecycle into Postgres with the declarative model to build, run, and monitor end-to-end AI workflows in one place with durability, retries, and production-grade execution built in. Now, to show you how AI pipelines work, I've asked Abe to give you a quick demo. Over to you, Abe.
Hey folks, I'm Abe. Today, I'll be using AI pipelines in HorizonDB to show you how little SQL code it takes to stand up a real AI pipeline directly inside Postgres. No external orchestrators, no glue code, just Postgres. So here's our starting point: a table with a few products in a store catalog. Now, watch how easy it is to make this table ready for vector search. The AI pipeline is fairly simple. It takes the data from the source, which is a document table, chunks the content, and then embeds that content using a text embedded model. And it's re-triggered every time the data is updated. That's the whole pipeline. Literally an array of steps. So now let's run the pipeline. Behind the scenes, our docs just got chunked, embedded, and dropped into a vector-ready sync table. To make it easier, I created this custom dashboard to visualize the pipelines and the steps. Let's check it out. As you can see, the pipeline was kicked up with several steps. Most notably, the embedding step took the longest time. Let's click into it. As you can see, it used the right model to embed. And then let's also see what happens after. And after that is run, we can see that the chunks were created and each doc has multiple chunks, just like we expected. Let's go back into VS Code and do the vector search. I'm going to search for wireless headphones for travel and focus work. And let's see what gets returned. As you can see, it returns the chunk text that's most similar to my query, as well as the related doc IDs. And of course, the first few rows return chunk text with things like headphones and noise cancellation. So this RAG pipeline definitely worked. Now here's the part I really want to show you. I'm going to go ahead and add a new row about Apple AirPods And let's see what happens to the pipeline. Pretty boring insert statement, right? Except the row is already being chunked and embedded. This is because we set the pipeline to run on table change. The pipeline notices that new row and processes only the delta, not the whole table. So let's run the set vector search again with Apple headphones. Nice. As you can see, AirPods come at the top because that row was automatically chunked and embedded in our database. And there you have it, an AI pipeline that reads like SQL, updates incrementally as your data changes, running in Postgres. These pipelines also support other complex workflows, such as data enrichment, approval workflows, and job scheduling. Everything you need to run a production-grade AI pipeline.
Now, to start wrapping up, I want to talk a little about how we're delivering tooling to make developers and database managers more productive on Postgres. About a year ago, we shipped a new VS Code extension for Postgres to help eliminate the constant context switching between building apps, optimizing databases, and just operating Postgres. It's available in the marketplace, works with any Postgres, and has some extra Azure integrated capabilities with support for everything from provisioning to monitoring and even migrating. It's been installed over 500,000 times in the last 12 months. We've got great feedback and asks from the community that we're shipping quickly to close some key gaps and increase functionality. As I mentioned, the extension works with any Postgres database, whether it's in any cloud, on-premises data centers, or even a local instance running on your laptop. It provides schema visualization, database context-aware Postgres code development, and real-time monitoring, where you can launch Copilot with automatic prompting directly from resource usage chart and let the AI do the debugging for you. And the extension is also deeply integrated with Azure, where you can natively provision both Flexible Server and HorizonDB directly from the extension using the same familiar flow as the portal. And you can also review and modify server parameters. You can manage server backups and even clone a server where you have the choice to clone without data, which is a great way to quickly snap a new server with the exact configuration and settings, or with data if you need a quick dev test platform. But one of my favorite new features is visual query execution plans. Developers can check their query plans directly in VS Code and see how the query is actually being executed, and use Copilot to explain steps or debug issues. This shortens the loop between observation and fix, and it's a fantastic application for AI to enable developers to move faster without requiring deep planner expertise. For Postgres on Azure, the extension becomes an operational control plane directly inside the development environment. Developers and operators can provision servers natively, adjust server parameters, clone databases without managing backups, or without leaving the editor. Ultimately, the result is a tighter feedback loop to build, observe, optimize, deploy, and operate Postgres using a single extensible tool, assisted by Copilot, and integrated with Azure when you need it. Now, to show you how all of this works in VS Code, I've asked Matt to give you a quick demo. Over to you, Matt.
I'm working on our order service dashboard, and the query to show top customer spend in the last 90 days is a lot slower than I anticipated. Let me run it. Over a second for a query that should be instant. Before I start guessing, let me see what Postgres is actually doing. I can open up the new query plan visualizer and see the plan in just a few clicks. Right away, I can see what the problem is. Let me check out this sequence scan on the orders table. I'll click on the node to get details, and looking at the conditions, I see this is my filter, and there's a surprising cast here. Let me ask Copilot what's going on. It looks like the created at column is stored as text, not a timestamp. I think this is probably from when we bulk loaded this table from a CSV. It worked fine back then, but now it's causing problems. So the fix isn't a new index, it's fixing the column type. Let me search for this table so I can find it quickly, and I'll open up the new Object Properties view to see if I can understand why this column is text and not a timestamp. Here I've got all the details about the table, including its definition and security properties. Let me check out the columns. Sure enough, it's a generated column that's computed from created at. I can't just change the type on created at. Postgres will refuse because this column depends on it. So this isn't a one-line fix. I'll have to drop, alter, and rebuild the index. It's not the kind of schema change I want to try on my working dev box. Since this is an Azure database for Postgres server, I can use our new clone server feature to create an independent copy of the server, including all the data, with just a few clicks, and test my migration there first. This is going to take a point-in-time snapshot of the whole server, so it'll take a few minutes to be ready. Great. Now that it's done, the clone server is automatically connected in my Object Explorer. So I'll just run the alter query that Copilot helped me write to change the column type. And once that's applied, I'll run the orders query without the cast and verify it works. Just over 200 milliseconds. That's what I was hoping for. Let's check the plan on this new query and confirm we've lost that expensive sequence scan. Looks good to me. I think I'm ready to apply this migration on my main server.
So we've covered a lot today, and this really reflects both our depth of investment in Postgres and the velocity that we're moving. In Postgres 19, we've committed many of our learnings to the open source project. We've added an array of new features to Azure Database for Postgres to improve performance, scalability, resilience, and manageability. And these aren't small changes. They're meaningful advances designed to help teams run Postgres with confidence, from the smallest workloads to the most demanding mission-critical systems. We also took a major step forward by making Azure HorizonDB available to everybody. With HorizonDB, we're rethinking what's possible for Postgres at cloud scale, bringing together elasticity, performance, and simplicity in a way that unlocks entirely new scenarios for modern applications. And on top of all of this, we've delivered new tooling that meets developers and operators where they are, simplifying operations, accelerating development, and giving teams deeper visibility and control across the entire lifecycle of their applications. This progress is the result of close collaboration with our customers, partners, and the global Postgres community. This is a shared journey, and today's topics are just the beginning of what's ahead of us. Thank you for spending this time with us today. We're excited about what's next, and we hope you enjoy the rest of the conference. Thank you.